We've talked a lot in this unit so far about how energy can transform from one form to another. And it's really important to also keep in mind another concept related to energy called the conservation of energy when that occurs. And when we say conservation of energy in physics, we don't mean just trying to conserve our electrical energy or going green or any of that kind of thing that environmentalists might promote. We just mean that it's a special law in physics that when we are converting from one form of energy to another, that energy is never created or destroyed when it's changing from that form to another. So we won't have any new energy suddenly appear out of nowhere, and the energy that we had at the start won't just disappear to nowhere either. So whatever energy we have in the initial stages is all going to be present at the end. It's just going to be converted into some new form. So a simple situation where we can play this out is through a pendulum. And a pendulum is just something that swings back and forth like on a string or from some kind of arm. And so here we have a ball that's swinging back and forth attached to some kind of string. And when it starts up at what we'll call position 1, it's at its highest point, and it's just sitting there at rest, ready to fall. So at its highest point, position 1, we can say that it has all gravitational potential energy because it's not in motion yet, but it's raised up to a certain height, and so it's got gravitational potential energy. Then it begins to swing downwards, and as it's swinging downwards, it gains kinetic energy. Eventually, it gets to its lowest point down at the bottom. At that lowest point, we'll call that position 3. And at that point, it's got no further that it can fall. It's the farthest that it could possibly fall, so there's no more height involved. So that means all of its gravitational potential energy has been completely converted into kinetic energy. So that point 3 at the bottom is where it's actually going to be going the fastest. And then, of course, from there, it wouldn't just stop. It would continue to swing back up in the other direction. What would be happening, though, at position 2? Well, at position 2, there's still some gravitational potential energy because it's still raised above a certain height, but it's also swinging. And so at that point there, it's a mixture of both. It's converted some of its original gravitational energy into kinetic, but it's still got some gravitational left over. So it's about half and half when it's about halfway down. So in general, we can see the energy is changing from GPE, gravitational potential energy, to kinetic energy. And this new conservation of energy law tells us that the total amount of GPE that it had at position 1 must be equal to the exact amount of kinetic energy it has at position 3. No new energy suddenly magically appeared out of nowhere, and the original amount of energy we had in gravitational form didn't just disappear to nowhere either. It was all converted into kinetic energy. We can analyze another scenario that will allow us to be a bit more mathematical in our approach to this. So imagine that we actually have a ball that's just rolling down a hill, and it starts from rest. We can then draw some approximate graphs of what the different forms of energy will be doing for this ball. So we'll first look at what a graph of GPE might look like, and then look at what a graph of kinetic energy might look like. So we can see for the GPE, it's starting at some total value and then decreasing all the way down to 0 gravitational potential energy. Kinetic energy is going to be doing the exact opposite. It's going to start at 0 and rise and increase up to some total amount. And the total amount that the kinetic energy has at the end will end up being the exact same amount that we had in gravitational energy at the beginning. What's even more important is to look at what happens when we put both of those factors together. So, of course, in general, we see that as the GPE is decreasing, the kinetic energy is increasing. But we really want to know, is energy being conserved along the way? And we can actually approach that mathematically if we look at what happens when we put them both together. So for this, it's actually useful if we maybe put some numbers attached to this. So I'm going to say that this total energy, of course, remember, is being measured in joules. And let's just put some imaginary numbers on it. So we'll say, of course, the bottom will be 0 joules. And let's say every line that we have on this graph goes up by 10 joules at a time. So I'm going to say 10, 20, 30, and this top line will be 40 joules. So what we're seeing is that at the very beginning, in this case, we'll say that the ball had 40 joules of gravitational potential energy and 0 joules of kinetic energy. So if we plot those 2 points out, 0 joules and 40 joules, if we add those two values together, we get 40 joules. And so we can plot a specific point right along this green line. And as I go through this, you'll see what this green line is really going to represent. If we go a bit farther in time, let's say we want to track this particular point in time. Well, at that particular point in time, we can see we have exactly 10 joules of kinetic energy. And when that's the case, at that same point in time, we have 30 joules of gravitational energy. When we add those two values together, that means at that point in time, in total, we get 40 joules. So that new black point that I've put at the very top on that green line is representing the total energy involved. At some later point in time, let's say right about here, well, the red and the blue actually intersect. And that's telling you that both the kinetic and the gravitational are each producing about 20 joules of energy. Well, 20 plus 20 is 40. So at that point in time, if we wanted to plot the total energy, it would really just be 40 joules still. And maybe a little bit later on, at this point here, we have 10 joules left of gravitational and 30 joules left of kinetic. When we add those together, we get, once again, 40 joules. At the very end, we're now at 0 joules of gravitational plus 40 joules of kinetic. When we add those together, we get 40 joules in total. So what's really important to make note of are the dots and where they lined up along the very top. So that green line then is really representing the overall trend that says regardless of what the individual energies are doing and how they're changing, the total energy remains the same. And that is the big take-home message that we can conclude from all this. So total energy remains the same. And that is exactly what the conservation of energy law is telling us, that whatever total energy we started with needs to be the exact same amount of total energy that we have at every other point throughout. No energy will magically appear from nowhere or disappear into nowhere. As we get closer to solving problems using this concept, it's also useful if we define a new concept called mechanical energy. And technically, mechanical energy just means a combination of different energies, but most commonly it means a combination of GPE and KE, the two that we've mainly worked with so far. And in general, when we solve problems using conservation of energy, all we need to think about is some initial position and some final position in time. And when that's the case, we don't really need to concern ourselves at all with what happens along the way going from our initial to our final points in time. It really doesn't matter. All that really matters is what total energy do we have at the start, and how does that compare to what we know we should have at the end. And that sometimes allows us to solve for unknown values, which is what we're going to do in the examples below. So in this question, we have a party clown that throws a ball into the air, and we're saying that it reaches a height of 8.2 meters, and we want to know the initial velocity that the ball was thrown with. So just to be a bit more specific, what we really mean here is that it's 8.2 meters above his hand, so above the clown's hand. So if I just draw a quick diagram of what that means, I'm going to draw an awesome stick figure here with some awesome party clown hair and a nice big long arm with a ball in their hand that they are throwing up in the air, and that maximum height that they reach is 8.2 meters in the air. When we set up given and required information, remember it's really important to separate out what we know about the initial stages of the ball and what we might know about the final stages of the ball. And so we're actually going to separate that out in a little chart. So on one side of our chart, we're going to put the word initial, and on the other side, we're going to put the word final. And you could call this an initial and final chart. I sometimes call it an HMV chart, though, because that tells us the three main variables that we should always record in these kinds of questions. H meaning the different heights that are going to be involved. M meaning the mass that might be involved. And velocity, of course, will represent V. But we need to be a bit more specific than that, because there's going to be some final height and some final velocity as well. So for height and velocity, on the initial side of things, we're going to call it H1 and V1. Mass really isn't going to change, though. So I don't need to call it mass 1, because there won't be any different mass later on. It'll just be the same mass. On the final side then, I'm going to write it as h2 for the final height. Mass will be the same, whatever it is, and v will be v2 in the final situation. And then we can think about things that we know from the question. Well, remember that with any kind of gravitational potential energy question, you can always decide and determine what you are considering the zero line for your height. So we could actually just measure height as starting from where the ball is actually being thrown. So we could say that the hand itself is the zero line. And that's a really powerful tool, because then we know that the initial height is really 0 meters. And that also tells us that the final height is going to be 8.2 meters above that zero line. We can also document some things about velocity in this case. Well, we know that at its highest point, the reason why it's its highest point is because it comes to a stop. So if we are just taking the final situation to be when it's at its highest point, which is why h2 is 8.2 meters, then at that point, we know that its velocity is going to be 0 meters per second. v1 we don't know, and that's actually the thing that we're asked to find. Now, what's tricky is the question doesn't say anything about the mass of the ball, and it also doesn't even ask us to find what that mass is. So for now, we don't actually know it, and we can't really use anything we have to find it right now. So I'm just going to leave a blank space there. You can just put a cross through there. We don't know mass right now. We'll have to see if there's some way we can solve this question without actually using mass. And we'll get into that as we go through. So when we go to solve these problems, there isn't any one particular equation that we can rely on that will solve every question related to conservation of energy. But there is a process that we can always follow. And the process is always started by giving a very general statement that tells us what conservation of energy really means. And here's the way that I like to write it. There are different ways you could write it, but this is my preference. I like to make a statement that ET1 equals ET2. So ET just is my way of saying total energy. So this overall statement is really just stating conservation of energy. It's saying that the total energy that I have in the initial stage needs to be the total energy that I have at the later stage. That's what I mean by ET1 and ET2. But then I can be a bit more specific than that, because total energy in our case so far really just means the mechanical energy, or for now, the gravitational and kinetic involved. So I'm going to call this EG1 plus EK1. It's my way of saying the initial gravitational plus the initial kinetic. And on the other side, EG2 plus EK2. The final gravitational and the final kinetic. The reason why I wanted to break it up into those pieces is because gravitational and kinetic energy are both things that I have specific formulas to help me find. So I'm going to just replace the e's in that equation with the specific formulas that calculate those different forms of energy. So, for example, EG1, I have a formula for that. It's mgh. But remember, specifically, if it's the initial gravitational, it's going to be using h1, the initial height. From there, what about initial kinetic energy? Well, I'm going to add that with another equation. Well, kinetic energy is 1/2 mv squared. But if it's the initial velocity, I'm going to call it v1 squared. On the other side, you can probably see where I'm going with this. For EG2, I'm going to use a special formula for that. I'm going to call it mgh2. So it's almost the same equation I used in the initial stage, but now I'm using the final height. And last but not least, for my kinetic energy, I'm going to replace that with 1/2 mv2 squared. So I know it looks like a very long and complicated formula, but it's all using things that we've worked with a lot before. And from here, we can actually simplify things quite a bit. The first thing we can do in a question like this is actually just a mathematical step. Because remember I said that the question isn't asking us to actually find the mass, and it also doesn't tell us anything about mass. So it would be really handy if mass could be completely eliminated from this situation altogether. And actually it can, because any time in math that you've got separate terms in an equation, if you have something that's common to every single term on both sides of the equation, you can cancel it out by just dividing every term by that. We have mass attached to every single term in this equation right now. And so if we divided both sides by mass, it would cancel out and eliminate mass from every single term. What this is actually telling us then is an important thing that's true in this particular situation, which is that our answer is going to be what we call mass independent, meaning that it literally will not depend on what the mass of the ball is. So whatever velocity we find for v1 will be the true v1 value, whether this was a tiny little golf ball that he was throwing in the air, or if it was a big heavy bowling ball he was throwing in the air. As long as he throws it with this initial velocity that we'll find, we know it's going to go 8.2 meters in the air, completely independent of its mass. So that's nice that that canceled out, but we can actually simplify this overall statement even further. Because what we can do is look at our given information and take a look at any zero values that we have, because zeros can be really handy. For example, we know that h1, or the initial height, was 0, which means that any term that involves h1 is going to become 0 when we plug it in. And so I'm going to represent that by crossing this term out with a little arrow and putting a 0 after that arrow. So I'm not just crossing it out completely to say that it just magically disappears. What I'm doing with that arrow and the little 0 is indicating that it goes to 0, or it becomes 0, when I actually start to plug values in. The reason being, of course, that h1 is 0, so the entire term becomes 0. For the same reason, if v2 is 0, any term that involves v2 is going to become 0 when I start plugging things in. So instead of even bothering to plug things in, I'm okay if you use that same little shortcut notation to just say it will go to 0 or become 0 when we begin to plug things in. And so both of those terms will completely disappear, not just the mass part, but all of them will completely disappear as soon as we were to go and sub things in. So we don't even really need to deal with them any further in this question. Let's take stock of what we still have left then. We still have 1/2 times v1 squared. Remember, I don't need the mass anymore because that canceled out. And on the other side, I just have g times h2. Again, mass was completely canceled out. It's v1 that I want to get all by itself, so I'll first get v1 squared all by itself by multiplying both sides by 2. So v1 squared is 2 times g times h2. Or in other words, v1 is really the square root of those things multiplied together. So I can plug in the things that I know. It's just going to be 2 times 9.8 times 8.2 meters. And I just need to make sure I square root that to find my final answer. So when we do all of that, we should get about 12.677 and so on, or approximately, if we're just rounding to 2 sig digs, approximately 13 meters per second. And again, just to summarize, that is a mass-independent value. So as long as the clown can throw the ball in the air at 13 meters per second as its initial velocity, that ball will go 8.2 meters in the air. And what's cool about that, as I said, is that it doesn't matter if that's a tiny little foam ball or if it's a big, heavy bowling ball. As long as the clown is strong enough to make it go up at 13 meters per second initially, it will go 8.2 meters in the air, regardless of its mass. We can now use the same process to try and solve for other variables as well. And so in the second example, we can use the same process, but now we can try and go through it a little bit faster now that you've seen it once. So we've got a 65 kilogram surfer that's riding a huge wave off the coast of Hawaii. And as he's traveling from the top to the bottom of the wave, we know his final velocity is 18.1 meters per second. And if he started from rest, because he was like totally hanging there, bro, how high is the wave? That's what we're trying to find. Well, again, It's useful if we try and doodle this out a little bit, even if it's not a very effective diagram, just so we can map out exactly what's happening. So we've got some big wave, and they've ridden down to the bottom of the wave. And so we know that when this surfer dude gets to the bottom of the wave, that's when his velocity is 18.1 meters per second. And that's going to be a final velocity. That's really a v2. What we're trying to find is the full height of the wave. So from the very top down to the very bottom, we are trying to find the height of that wave. And I guess I should put some arms on my little surfer to make sure he stays balanced as well. From here then, we can set up our initial and our final variables. And you don't even need to write the words initial and final if you don't want. You can just write I and F from now on. So remember, initially we call those variables h1 for the initial height, m will be for mass, and v1 will be our initial velocity. Then we have h2, m, and v2. Well, what we can do again is decide what our zero line is going to be for height. So why not just use the very bottom of the wave? So this could be our zero line. That line that they end up at the bottom of the wave. That's effective because that tells us what h2 is. It tells us that h2 is 0 meters. That means that whatever height it started from must be the entire height of the wave itself. If that tells us how many meters it is above the zero line, that'll tell us the total height of the wave. So if we can find h1, we'll know the height of the wave. So that's actually our required piece of information. The mass at the start is 65 kilograms, and we're going to assume that this surfer did not go through some kind of weight loss program as they were traveling down the wave, and so when they get to the bottom of the wave, they're still going to be 65 kilograms, and that's part of why we don't bother even putting m1 or m2, we just call it m for mass. And in this case, we actually know it. The initial velocity is not directly stated, but it does say that he started from rest, because he was like totally hanging there, bro. So that tells us that we have 0 meters per second as our initial velocity. Our final velocity then must be the 18.1 meters per second that is stated directly in the question. So from here, we're going to set things up in the exact same way that we did before. No matter what the conservation of energy question is, you can always start with the very general statement of conservation of energy itself that says that whatever total energy we have at the beginning must equal exactly the same amount of total energy at some later point in time. And so, of course, the initial stage for us is when he's at the very top of the wave. The final stage is when he's down at the very bottom of the wave. From there, once again, we'll break those total energies up into their separate pieces. So there's going to be some gravitational and some kinetic, possibly, in the initial stages, and some gravitational and kinetic in the final stages as well. From there, we can even take those specific energy values and list them as their formulas that we can use to calculate them. So we'll say that that's mgh1 plus 1/2 mv1 squared. On the other side, we have mgh2 added with 1/2 mv2 squared. From here, what we did in the previous question was cancel out the mass, which you might think we don't want to do in this case because we actually know mass, so that's useful. And in fact, we could use the mass and we could sub it into this equation exactly where you see mass. But again, we don't actually need it. And it's a little bit redundant to plug it in and use it in every single equation if we can actually cancel it out. And so even though we have it, doesn't necessarily mean that you have to use it. If you want to, you could try this question out using mass and plug it into all 4 terms, but what you'll see is that you'll actually get the exact same answer that we would get if we just cancel it out, which is what I'm going to do now. So I'm still going to cancel out mass just to make it easier for me to substitute things in. Simplify it as much as I possibly can. Remember, the other thing we can do to simplify is look for any 0 values. And we have a couple of those once again. So we have our initial velocity is 0, so that means anything that involves v1 must go to 0 as well. So this term won't just magically disappear, but it's going to become 0 when we plug those values in. So I'm just going to eliminate it now. And we also know that h2, or the final height, is 0. So this entire term I'm going to eliminate now because it's going to go to 0 when we plug things in. In our next step then, let's take stock of what we still have left. We have g times h1 is equal to 1/2 times v2 squared. h1 is what I'm actually trying to solve for, so I just actually need to divide both sides by g. So there's a couple different ways you could write this, but I'm just going to write it as h1 is equal to v2 squared over 2 times g. Because 1/2 v2 squared is really the same as taking v2 squared and dividing it by 2. So if it was already being divided by 2 and then I also divide it by g, then I can just write it in that way. So it's v2 squared divided by 2g. Means the same thing. Now I can just plug in the things that I was given. So that's 18.1 meters per second, and that whole value needs to get squared. And then I divide that by 2 times 9.8. When we do all of that, we get about 16.714 and then a bunch of other stuff. What I'm going to do, though, is round that off to 3 sig digs, because even though mass was only given to us with 2 sig digs, we didn't actually use it at all. So the only measured value that we used was the 18.1 meters per second, which actually had 3 sig digs. So I'm going to round this off to 16.7, and remember that that's a height. So specifically, that's 16.7 meters. So it's telling us that the total height of the wave, or the height that the surfer started from, was 16.7 meters. The final example about the glider is one that you can try on your own, but we're going to do in more detail in class. And there's actually 2 different ways that you could go about solving the problem, and I'm going to show in class why those 2 methods are actually equivalent, but there is one that takes a few less steps than the other and can be a little bit easier. So you're welcome to try that on your own, but as I said, we will take that up in class.